When you hear the word chemistry, you probably picture bubbling beakers or maybe those complex carbon chains from biology class. But most of the world, I'm talking about the screen you're looking at right now, the rocks under your feet, it's all built from something else. So today we're diving into the huge and super important world of inorganic chemistry.
So what's the connection? A phone battery, a cancer drug, and clean air. The answer is inorganic chemistry. It's this incredible field where scientists carefully pick and choose elements from all over the periodic table to literally build the world around us.
So what exactly is inorganic chemistry? Well, think of it this way. Its famous cousin, organic chemistry, gets all the attention for focusing on carbon, the building block of life. But inorganic chemistry, it gets to play with everything else. The entire periodic table, over 100 different elemental ingredients that form the backbone of our planet and all our technology.
Okay, so here's our game plan. We're going to start with the ultimate set of building blocks, then learn the basic rules that make them tick, and then, this is the fun part, we'll see a wild exception to those rules. From there, we'll see how chemists use all this knowledge to power our world, heal our bodies, and even design a cleaner future.
First up, let's talk about the ultimate building blocks. And for this part of the journey, our guide is probably the single most important chart in all of science.
You guessed it, the periodic table. You can think of it as a recipe book. Every single element, from lithium all the way to platinum, has its own unique personality and properties. The job of an inorganic chemist is kind of like being a master chef. They have to select just the right elemental ingredients to create materials that do exactly what we need them to do.
Of course, to be a good builder, you have to know your materials. So let's look at the patterns, the fundamental rules of the game that let chemists predict how all these ingredients are going to behave.
Here are two of the biggest rules. As you move across the table from left to right, atoms actually get a little smaller, but they get way better at grabbing onto electrons. And as you move down the table, they get bigger. These predictable trends are like a chemist's superpower because it lets them make really good guesses about how different elements will react and bond together.
But, chemistry loves to throw a curveball, and this next one is a huge one, a really strange wrinkle in the rules that has massive consequences for a whole bunch of important metals.
It's called the lanthanide contraction. It sounds complicated, but here's the gist. As you move across that special row of elements at the bottom of the table, their electrons are in these weirdly shaped orbitals that are terrible at shielding the outer electrons from the pull of the nucleus. The result? The whole row of atoms gets squeezed tighter and tighter, becoming way smaller than you'd expect.
And here is the perfect example of why that matters. Look at zirconium. Right below it on the table is hafnium. Now, according to the rules, hafnium should be a lot bigger, but because of that lanthanide squeeze that happens right before it, it ends up being almost the exact same size as zirconium. This crazy coincidence makes them super hard to separate and gives them really similar chemical properties, which is a huge deal in materials science.
All right, so we've got the rules and we've got the exceptions. Let's start building something real with it. We're going to talk about batteries, a perfect case study in how chemists choose very specific elements to solve a very specific problem: portable power. We all hear the term lithium-ion battery, but that's really just a category, kind of like car. The real secret sauce, the thing that decides how powerful, how safe, and how long-lasting that battery is the specific blend of inorganic metals inside its cathode. That choice is everything.
And chemists have developed different recipes for different jobs. For your phone, you want to cram as much energy in as possible, so you use lithium cobalt oxide. For an electric car, you need a good balance of power and a long life, so a nickel-manganese cobalt blend is a popular choice. But for, say, heavy industrial gear, where you need maximum safety and thousands of recharges, lithium iron phosphate is the absolute champion because it's so incredibly stable.
Okay, from powering our machines, let's get a bit more personal and talk about healing our bodies. This is an incredible story of how inorganic chemists built one of the most effective anti-cancer drugs in history, all based around a single heavy metal atom.
The drug's name is cisplatin, and right at its heart, literally, is a single atom of platinum. This isn't some huge complex organic molecule. It's a deceptively simple, inorganic compound that completely revolutionized chemotherapy. And how it works is both ruthless and brilliant. Cancer cells divide really fast, so they soak up the cisplatin. Once it's inside, that platinum atom physically latches onto the cell's DNA, creating a kink, a bit of damage. The cell tries to fix it, but it can't. And that unfixable damage triggers a self-destruct command called apoptosis. It is a precision strike, all made possible by the unique chemistry of that one platinum atom.
So we've seen how inorganic chemistry powers our tech and heals our bodies. Now let's look at what's next, the absolute cutting edge. A brand new class of materials that's basically the ultimate in custom chemical construction.
They're called metal organic frameworks, or MOFs for short. The best way to picture them is like an atomic scale set of Legos, or maybe a molecular sponge. You have metal atoms that act as joints, and they're connected by these organic linker molecules. What you end up with is a crystal structure that is mostly empty space.
And that is what makes them such a game changer. As this quote puts it, MOFs are breaking down the old walls between organic and inorganic chemistry. They're taking the best of both worlds, the rigid structure from inorganic metals and the custom functionality from organic chemistry, to create something totally new.
And the properties you can get are just astounding. MOFs have the highest surface areas of any material ever made. A single gram can have the internal surface area of a football field. You can tune the pores with insane precision to trap one specific type of molecule and ignore everything else. This opens the door to unbelievable technologies, like pulling CO2 straight out of the atmosphere, or even harvesting drinking water from dry desert air.
Which really brings us full circle, from the basic rules of the periodic table all the way to these wild designer materials like MOFs. Inorganic chemistry is all about building. It's about knowing our elemental ingredients so well that we can combine them in new ways to solve our biggest problems. The recipe book is wide open. The only question is, what are we going to build next?